Okay, so let's stare at this map of currents for a minute, and we'll also see this as an animation. Plus, I'll show another animation from NASA, which shows how complicated the circulation actually is. Okay, so let's start in the deep tropics, where we have the trade winds pulling the water from east to west, especially in the Atlantic and Pacific Oceans. So you expect currents to be from east to west, and sure enough you see something called a south equatorial current, which is going from near Galapagos towards New Guinea, and in the northern hemisphere you have another current called the north equatorial current that is going also from off the coast of Central America towards the Philippines. Okay, so trade winds blowing from the southeast and northeast, pushing water westward. You expect westward currents, and you have two westward currents that are quite predominant. What is surprising, remember we had the concept of intertropical convergence zone, which means as the southeasterlies and northeasterlies were coming across and meeting in the intertropical convergence zone, we had equatorial doldrums, right? Winds are kind of very weak on the equator. So what happens? The water that's getting pushed westward actually piles up on the west coast against New Guinea and Mindanao, Philippines region. And remember, mound of water is gravity, so water flows down the hill. So you have water piling up here in the west, water flowing downhill towards the east into the ocean. Coriolis acting is going to push it to the south towards the right. If you are going east, it's going to push you south. To the south you have the equator, because equator is a dynamic boundary, which means Coriolis goes to zero on the equator. It's the opposite direction in the south and another direction in the north, which means equator is not easy to cross for the ocean unless you have friction that is pushing it across, right? So equator, just remember, acts as a dynamic boundary. It also acts as a wave guide. It can transmit waves across because of its dynamic boundary kind of nature, because of the change of Coriolis across. So it is this piling up of water because of westward flow and flow down the hill that you get this peculiar current called the equatorial countercurrent. Countercurrent because winds are going east to west, but the current is going west to east, which means it's flowing into the winds. Of course, the doldrums, weak winds, but nonetheless, it's flowing into the winds. You can also see an equatorial countercurrent in the Atlantic, and you can already see that the one in the Pacific is much more coherent because it's a bigger ocean, bigger fetch, bigger pile of water, and so on, that is driving the countercurrent. In the Indian Ocean, because of this asymmetry, you can see that the equatorial countercurrent is actually south of the equator. Okay, why doesn't water pile up in the south? We will see that the southeasterly trades begin to end by the time you reach the western boundary. So there is asymmetries in not only the ITCZ, but that asymmetry is of course driven by the asymmetry in the winds, southeasterly and northeasterly trades themselves. So you have this clockwise gyre in the northern hemisphere consisting of the Kuroshio on the western side, California current on the eastern side, and the Kuroshio extends into the North Pacific and becomes the North Pacific current. And remember, the mid-latitude westerlies and the polar easterlies, they also create a weaker gyre called a subpolar gyre, which is seen here as a subpolar gyre in the Gulf of Alaska, here in the Greenland, Iceland, Norwegian seas way to the northeast in the North Atlantic. Similar structures exist in the south with more complicated flow in the Southern Ocean. So look at each ocean separately, so don't worry too much. I didn't go into all the details, but the main thing to remember is that the trade winds pile up water on the west and create this peculiar current going into the winds appropriately called the countercurrent, and it's in the equatorial region, so they are referred to as equatorial countercurrents. Exist in all three tropical oceans, and the gyres are clearly seen: North Pacific gyres, South Pacific gyre, North Atlantic, South Indian. There are subpolar gyres also in the southern hemisphere, more broken up because of the difference in the structure of the Southern Ocean compared to the Pacific and Atlantic Ocean. There are also cold currents coming down, so you have warm currents going north and cold currents coming south to the north of the warm currents going north in the western boundary. So you have the Labrador current here, you have the Oishio current here, and the equivalent of the eastern subtropical gyre current, boundary current, is the Canary current in the Atlantic Ocean. In the south you have the Peru current and the Benguela current. On the west you have the Brazil current, East Australian current, and so on and so forth. So we will learn about these asymmetries: warm water going north in the western boundary, cold water coming south in the eastern boundaries. They are not similar currents, they have very different structures, which again goes back to how the ocean integrates the wind forcing and how the Coriolis force changes with latitude, and what kind of circulation and rotation is being put into the ocean by the wind. Very nice concepts, sound complicated, but actually they are quite simple, so you should watch these as many times as you need to make sure you understand the concepts, because western boundary intensification is going to be one of the most important concepts in oceanography that you will learn.